첫 번째 연사로는 레드테스트 대표님이신 리차드 샤프 박사님께서 범용 방사선 및 테스트 분석을 위한 femto 레이저 시스템에 대해 발표하도록 하겠습니다. 샤프 박사님은 영국 사우스햄튼 대학교에서 양극성 트랜지스터에 대한 방사선 효과에 관한 박사 학위를 취득하였습니다. 우주, 원자력, 의료 및 고에너지 물리학, 응용 분야 전반에 걸쳐 방사선 효과에 대한 30년 이상의 경험을 바탕으로 최근 레드테스트를 설립하여 이온화 방사선 관련 문제에 직면한 사용자에게 독자적인 방사선 테스트 자문과 서비스를 제공하고 있습니다. 오늘의 발표에서는 레이저 싱글 이벤트 이펙트 테스트 시스템의 장점들을 소개합니다. 레이저 시스템을 통한 방사선 테스트 범위는 대형 우주선에서 소형 위성, 그리고 지상 레벨의 자동차 및 철도 엔진에 이르기까지 다양합니다. 샤프 박사님을 환영해 주시길 바랍니다.
Hello everyone, and welcome to this presentation at the ASIC 2022 conference. My name is Richard Sharp and I represent Radtest Limited. We are an independent test house located in the UK, specializing in measuring and characterizing the effects of ionizing radiation on electronic components and materials. We focus particularly on the space sector, but we have significant activities also in the nuclear, high energy physics and industrial spheres as well. The final thread of our activities is the manufacture of the Serial 2 laser single events test system. And the use of that type of system is going to be the subject of this presentation. I'm honored, very happy to be invited to present at ASIC 2022. It's a well-known conference. I've never had the opportunity to participate before, so I'm very appreciative of that chance this year. So the title of my presentation is Femto-second Laser System for General Purpose Radiation Test and Analysis. And I'm not going to focus so much on the technology of laser single event testing, but more about how that technique can be used to inform and provide data for assessing the likely response of components to the radiation environment in space and in other applications where ionizing radiation can present a problem and lead to vulnerabilities in those components, giving problems in the application. So thinking first of all about space, what do we know about the environment? Firstly, I think everybody is very familiar that space is not a very pleasant environment. It's a hostile environment in many ways. Firstly, you have to get there. You have to put your satellite into orbit and go through all the rigors of the launch process. Extreme acceleration, vibration, and shocks. It's worse than the worst roller coaster ride you've ever taken. It's a very extreme physical process that the satellite has to endure in order to reach orbit. And then once it's there, then there's all these external factors come in. Vacuum, temperature, very extreme temperatures, very cold, very hot, sometimes cycling between those extremes. That cycling in itself can give reliability problems. Of course, radiation, we'll hear much more about that shortly. And of course, if you have a problem, if you have a breakdown in orbit, then it's very difficult to effect any repairs to that satellite. So focusing a little more on the radiation side, this I acknowledge NASA for this slide. I think it's a very neat illustration of the Van Allen belts around the Earth, the well-known regions of the near space environment where there are elevated levels of radiation in two belts. The smaller inner belt closer to the Earth, largely protons, and then a much larger outer belt that is has many more electrons, but also some protons trapped within it. And these regions are held there by the Earth's magnetic field. Most of the particles come from the sun, and they are then held in these regions as a result of the Earth's magnetic field. Now, the inner belt is a few thousand miles above the surface of the Earth, and therefore it's above most of the low Earth orbit region where we place satellites. Although both of these belts, the whole space environment around the Earth is very dynamic, and so even satellites in low Earth orbit will see some radiation from the inner belt from time to time. Also, the Earth is not a perfect sphere, and so there's one region of the inner belt that comes particularly close to the surface of the Earth, and this is located over South America and leads to a region, an area where there tends to be higher radiation effects in orbits. That's termed the South Atlantic anomaly. Now, satellites that are further out in MEO or in geostationary orbit have to pass through the inner belt and also the outer belt, and there's a risk of greater radiation dose accumulation in that process. That's becoming more serious as more people are looking at electric propulsion to move satellites into higher orbits. Then the time to reach that higher orbit is longer. The dwell time in the outer radiation belt is higher, and that can lead to higher doses. Of course, what's not shown on this image is the impact of cosmic rays. These come from outside the solar system, and they are pervasive. They cover, they're really not influenced by the Earth's magnetic field very much at all, and therefore they're present throughout the environment. So, okay, there's radiation. Now, what do we know about radiation? What are the risks associated with that? What do satellite designers have to take into account? And there are two principal effects involved. One is the charging of insulating materials, and what happens in that situation is that an insulating material gradually accumulates more and more charge, and eventually that charge will exceed the breakdown voltage of the material, and it will have a spontaneous discharge. That can give structural problems as well as ESD issues. That's all I'm going to say on that issue. It's not the topic of this talk. The second effect that is much more relevant here is the degradation of materials, particularly electronic components, as a result of radiation exposure. And we divide that radiation damage into two categories. First is the classic long-term accumulative effect of dose, of total integrated dose, sometimes called total ionizing dose, but integrated over time gives you the dose that the sample has received. And these effects tend to be permanent, or at least very long lasting, and therefore they're more serious for long duration missions and for missions that are in areas where there's high levels of particle radiation in space. The second type of effect to talk about are due to the interaction of one single very energetic particle with typically the electronic component. And these are classed as single event effects, very often due to cosmic rays, but there are some components that are susceptible to single event effects due to protons as well. It's a very rich field. There are many, many different types of single event effect that can be seen on devices. Some of these are temporary and disappear almost as quickly as they arrive. Others are permanent and very damaging to the component. So whilst a short duration mission, maybe one that's only in LEO, may think that radiation effects are really not a problem for us. Actually, these single event effects are just as relevant there as in any other orbit. And the most significant type of event that a single event can lead to is a latch-up. And this is just as relevant for a CubeSat that's due to be orbiting for a few months as it is for a ComSat with a 30-year lifetime. So what is a latch-up? SEL, single event latch-up, is a phenomenon that's known at ground level. It's been well understood for many years in general electronics design. Usually, if a circuit has not been designed very well, then latch-up can occur. But the techniques for avoiding that are very well known. The problem is that in space, a cosmic ray can induce this latch-up process much more commonly than would be the case at ground level. The problem with latch-up is that it leads to a very high current flow, so very rapid increase in the temperature of the die, and within a fraction of a second, typically leading to thermal destruction of the part. It's the most rapid, destructive, damaging effect that could happen to a satellite. And you can see from the plots here that when the voltage on the device exceeds a critical initiation level, then the part starts to go into the latch-up process. The current begins to rise, slowly initially. The voltage falls back a bit as the current rises. But once the current reaches a certain threshold, then it increases very rapidly indeed. And unless you mitigate that, then it's goodbye to that part. The right-hand graph shows the measured evolution of the current for a device during a test, during a single event test. Current is on the vertical axis and time on the horizontal axis. You can see that the current is fairly stable for the first half of the time. It then increases in a couple of small steps, but it's still a moderate level. And then suddenly at around 4 seconds, the current very rapidly increases. Now, in this case, we had some mitigation in place, and the power supplies were turned off, and the current was limited before it became damaging. And you can see here the very rapid recovery from latch-up. If you catch a latch-up, turn off the power to the device, and then restart the device in a fraction of a second, then it will go back. It will very often go back to the pre-single event effect condition until the next one comes along. So that describes a latch-up. And so the key tactic for dealing with latch-up is to avoid that very rapid, very large increase in current. So there are several mitigation techniques, protection that can be implemented to avoid latch-up. Firstly, you can apply the same technique that's used at ground level very commonly to build some additional circuitry around your component to detect and prevent the latch-up occurring in the first place. The negative side of that for space is it tends to add size, weight, area, power consumption to the payload. That's undesirable. It also increases the complexity of the software involved. So a second technique is to choose parts that are known not to suffer latch-up. You may have that knowledge through having flown the parts before. Flight heritage is always very helpful. You may choose to use parts that are guaranteed latch-up free by their design. Radiation hard design will normally use techniques, technology, materials that are known not to suffer from latch-up. Or you may have test data from a commercial part, been tested and been demonstrated, been shown to be free of latch-up. All of those are valid routes to take for selecting parts that you know are not going to suffer latch-up. There's a question mark over how you deal with COTS parts, of course, because traceability of components is very important. If you have data, if you've conducted testing on a part, then when you come to use that part in your design, you need to have absolute confidence that you're using the same part that you have tested. And if you have that traceability, great, that's perfect. If you don't have that full traceability, which is very commonly the case with commercial parts, then maybe your data are valid, maybe they're not. So you have to perform, in that case, you have to perform some kind of risk assessment and to determine the likelihood of a latch-up occurring. And calculating that risk, making that assessment when you have no data, no test data, no performance data on your parts, it's a very difficult exercise to complete. Obviously, you can go and test, you can buy that data from the manufacturer in some cases, but that costs money. So in order to mitigate this risk, you have to spend some money. And for particularly lower budget missions, that is quite difficult for them. And especially for a lot of CubeSat missions, for example, then people tend to ignore the problem, ignore the risk, and hope that they're lucky and don't suffer the problems. And a lot of the time, they get away with it. Satellites don't suffer latch-up, they don't suffer radiation effects. If you happen to have a mission that's a relatively short duration, going into the right orbit at the right time in the solar cycle, and you avoid storms and so on, then you can get away with it. Other times you may not be quite so lucky. So there are different approaches there, and an individual mission has to determine what is the right approach for them. The classic approach for trying to ensure that you avoid latch-up, whether it's part of the rad-hard design process or generating test data for a specific mission, is to undergo single event effects testing. And there have been developed a number of standards or test methods for guiding this testing to try to instill some kind of standard process, particularly to allow the intercomparison of data from different groups at different times. And I've listed some of those standards and methods on the slide. These cover measurement of all the different kinds of single event effect that can occur, the most common ones being upsets, latch-ups, transients. For more complex devices, functional interrupts of many different kinds, and for MOSFETs and similar devices, burnout and gate rupture are serious problems. As I mentioned earlier, these can be caused in space by both heavy ions and protons, and so we have test facilities for both available. Some of these facilities are listed here, the ones that are commonly used in Europe and the US. There are others, but these are the principal facilities that many people will be familiar with. But these are expensive facilities to use. They're very popular, and so the cost and time of performing single event testing is something that tends to be used more by the bigger, higher profile, more expensive missions, and less so by other missions. I'm going to show you a couple of pictures now from some single event testing we've performed over the years. On the left-hand side of this picture, I'm showing a test of a microcontroller device. It's in master-slave configuration, and you can see here the device under test is the lower of the two boards in the fixture, and this was taken at TAMU in the US, where we were testing with a very high LET gold beam, looking at the effect on the microcontroller. And on the right-hand side is an image from the heavy ion facility at Université Catholique Leuven in Belgium. And this was during a test of a large FPGA device. That device is on the lower part of the board. This FPGA is so large that you can see the die very clearly in this image. and it's the grey rectangle towards the bottom of the circuit board in the middle of the image. And you can see there that the device has been prepared, that the lid has been taken off of the package to expose the silicon, which is necessary for heavy ion testing. And also necessary for this kind of device is that the silicon die, the thickness of that die has had to be reduced, because even the highest energy, the greatest, highest energetic particles that we can produce at ground level with the accelerators we have are unable to penetrate the package of devices, whereas in space the energy levels are so much higher that they are able to go right through the whole spacecraft. So even if the device is packaged in space, it's not protected from these particles. So what is the problem with single event testing? Why don't we do it all the time? Heavy ion testing is certainly the gold standard approach to determining the impact of single event effects on a component, or the vulnerability to. However, beam time is scarce. There aren't that many facilities. There are lots of people who want to use them. These facilities are used for a lot of other purposes as well. And as a result, the beam time is expensive. You may have to wait a long time before a slot is available for you, perhaps up to 6 months. Even then, if you're unlucky, you turn up, you travel to the facility, you turn up, you have your samples ready to test. Accelerators are big, complex machines, and they can break down, and you may miss your turn as a result of that. So even with normal single event testing, there are disadvantages, there are risks associated with it. And nowadays, many commercial missions, which are driven by fast delivery, fast turnaround, they don't have the time or money for that kind of approach, and need to find a different way of dealing with it. And that's where lasers come in. So let's start talking about lasers. The great advantages of using a pulsed laser to measure single event effects are going to be the topic of the rest of my presentation. The reason we use pulsed lasers is that the way in which the energy is delivered to the device, the dimensions of the track, the size, the interaction, the charge densities, all those parameters are very similar to the interaction of a heavy ion with the device. So the use of a laser is representative of an ion strike in space. And if you have your own single event tester based upon a laser, which is absolutely possible, whereas very few organizations are going to spend billions on a cyclotron of their own. If you have your own laser single event effects tester, then you have full control of the testing process. You can do the testing when you want to do it. You don't have to wait months for a slot. You can use as much time as you want. When you go to a cyclotron, you're paying perhaps £1,000, dollars, euros, whatever currency you wish to use every hour. Whereas with your own system, obviously the running costs are much lower than that, and you're able to afford to use many, many more hours time on the machine. That enables you to try different configurations, different bias arrangements, different ways of using the device. Don't have travel costs to the accelerator facility, and overall there's a much more affordable cost of ownership of the laser. Now, in terms of using a pulse laser for testing, then there are no existing test methods for laser single event effects testing. There are some in development. We're expecting to see one, for example, from the European Space Agency in the next year or so, which will provide some guidelines for this kind of testing. But at the moment, there are none. We have to try and adapt the heavy ion test guidelines for use with pulse lasers. You can use a pulse laser to measure pretty much the whole range of single event effects, latch up, upsets, transients, burnout on MOSFETs. What you cannot measure is gate rupture. The mechanism there is different, so that's probably the one type of effect that you can't measure with a laser system. I've said before that the using a laser is quick, it's flexible, it's affordable for many more teams than is a cyclotron. And this, particularly the access to faster results, means that using this technique enables many more missions to access radiation effects data that might not otherwise consider doing so. Now, it's not a panacea. There are limitations to what one can do with laser testing, and perhaps the best known of these are that the laser pulse will not pass through opaque structures within the device, particularly metallization. So if you have a very complex device, multiple layers of metal, then that is going to be more difficult to test with a laser than a simpler device. There are some techniques for overcoming that. You can cause the laser pulse to impinge on the sensitive area from the other side of the package, perhaps. Depends on the package style and the mounting arrangement. So there are ways of addressing that. But certainly for stacked devices, some the more complex, more recent developments, then it's going to be quite a challenge to test those with a laser. So there will always be an application for cyclotrons, there's no doubt about that. The other drawback of laser is that there is no generic conversion available between laser pulse energy and linear energy transfer from particles. It's possible to develop that relationship for a given technology, a different type of device, but it does require data from both techniques in order to perform that cross correlation, which kind of defeats the object of that. So laser testing gives you very good qualitative data. You can make very accurate and effective comparisons with laser data. But if you want to have quantitative upset rates, NET thresholds, then you do need to perform some kind of correlation or calibration of those results against real heavy ion data. I've summarized these pros and cons in this table. There's a lot of information in this table, and I'm going to go through some of that now. What I'm comparing here is the effectiveness of, first of all, an ion beam cyclotron approach for each of these topics. Compare that with the lasers, and I divide the lasers into two kinds, two flavors, if you like: single photon, two photon absorption. I'm not going to go into the detail of that because that's the subject of a separate talk or presentation at this conference. But there are some differences with what one can achieve with an SPA and TPA system, and I'll pick up on that in a moment. One of the really, what for me is probably the most fantastic benefit of using a laser system is for the screening of devices, particularly screening large numbers of devices, to be able to rank in their sensitivity to single event effects a number of different candidates for a certain functionality in your circuit. You can do that very effectively, very, very easily with a laser system, and you simply would not have the time to be able to do that with an ion beam system. If you have 10 different components for a certain function in your circuit, you're not going to test all 10 of those with an ion beam. It's too expensive, it takes too long. But with a laser, you can run through those very easily and then determine which are the best, which are the worst. You may then choose to take the best one or two candidates and go and verify that performance with a cyclotron. That's fine. But at least the laser will then have enabled you to select the best candidates so that you're not wasting that scarce and expensive resource of heavy ion beam time on a part that's going to fail. But screening is a fantastic application of laser testing. I've already said that if you want to obtain quantitative data on LET, then you cannot do that with the laser very easily at all, but you can do that with the ion beam, so that's a clear advantage of the ion beam. Mapping single event sensitivity. This is a topic that's really valuable for manufacturers of devices or for people working with, for example, FPGAs who are interested in whether there's any variation in the sensitivity in different regions of the device. There are one or two microbeam ion beam facilities around, but they are even fewer than normal ion beam facilities. So it's even more difficult to obtain time on those machines. But it's inherently part of the way in which laser test systems operate. That data just fall out of the laser test process. So being able to map the variation sensitivity of the device across its area is something that is inherent in the laser testing process. Slight advantage of the TPA system is that you can do that perhaps more easily in 3 dimensions as well as 2. Rad-hard product development, you can use all of these approaches for that. Again, benefits of lasers are that you have more time available more quickly, more cheaply, so you can speed up your development cycles compared with using an ion beam machine. Similarly, in exactly the same way, you can look at some other phenomena that happen in devices. But for some of these phenomena, they do not occur very often. They're rare events. And if you have some rare events that are actually very high impact, that have a huge impact on the functionality of the device, then you may not spot those during heavy ion testing. You may not have enough beam time to even see whether those occur. With the laser system, you can run the test for hours and hours, days if you wish, and you can start to build up really robust statistics over the likelihood of these events occurring and their impact on devices. So it's kind of rare CEFIs that don't see very often, but could be very, very significant for the functionality of a payload, with a much better chance of spotting and calculating rates with a laser system. And we've already talked about the other 2 topics there. So let me move on to pictures. And I'm showing here a Surreal 2 laser event test system that we built a few years ago now. This is a TPA system, so you can see on the left-hand side, the laser. Then there's an optical parametric analyzer for changing the wavelength of the laser. That enables you to look at different materials, but also to perform both single and 2 photon absorption with the same piece of equipment. And then inside the large black box, that's the business end of the system where the movement stages are located that you place the sample. Let's have a look inside there. And this was during construction of the system, and you can see that there is a stack of movement stages, XY movement stage at the bottom, lift stage, there are goniometers there, you can have a rotation stage if you wish. On the top of this one, there is a piezo stage for giving arbitrary movements over a small area to give you the option to have some complex scanning arrangements. And then you can just about see 2 objective lenses peeping out from behind the periscope, leading up to the top shelf where most of the optics are located. And they're located there as a visible camera and an infrared camera, as well as all the optical elements. The infrared camera is really useful for TPA, where you a lot of the time you're probing into the depth of the silicon die, and this enables you to see into the device, to look for structures within the device, and to put the laser pulse in the right place to investigate the structures in which you are interested. Now that's an overview of what a system can look like. I should say that these systems are very, very configurable. No two systems look the same. Every one we build is different, and the process of identifying what is the right configuration for you is a conversation to have at the beginning of the purchase process, so that you ensure that the system that you have delivered meets your needs rather than some standard tick list of capabilities. One of those aspects to consider is the type of scanning you wish to perform. The classic case is shown on the top right-hand side of this slide, where it's a raster pattern or snake pattern, and you scan the beam linearly, change its direction, come back, and move backwards and forwards over the area of the die in that way. That's straightforward, it's simple to do. However, if you want to maximize the throughput of your system, to really speed things up, to generate the results of the screening process as quickly as you can, to make it as efficient as possible, then your scanning has a few criteria that really should be associated with it. You want a constant scanning speed. You want a smooth trajectory with really minimal acceleration, because that will give you an even distribution of the laser spots across the surface. You can see on the raster scan plot there that the speed of movement changes when the direction of scanning changes. So you tend to have clustering of laser spots at the corners and on the short sides of the scan. This is because the laser is pulsing at a fixed rate, and when the movement stages speed up and slow down, then the distribution of those laser spots it becomes non-uniform. So one approach that we offer is a spiral scan, and the lower right plot on this slide shows the distribution of the laser spots across the device when using a spiral scan. And you can see here that they're much more evenly distributed, and that makes calculation of rates, investigation of different rates in different parts of the device more straightforward. And in the same way as a raster, you can tessellate these across the surface of a die to cover the region of interest. So some examples. Probably the device that is best known in terms of laser systems is the LM124. This is a quad op amp, very well-known device, and it's become a sort of benchmark for laser test systems. And what I'm showing here is one of those devices. There's a micrograph of the device itself on the top right. On the bottom right is an image showing a spiral scan overlaid on top of one of the transistors on that device. It's Q6, which is in the middle towards the top of the upper picture. And the spiral here has been overlaid across that transistor. The red circles on this image show the magnitude of the transient response of the device to the laser pulse. And you can see on this one that the larger diameter circles, the greater response, tend to be where the silicon is located, and those spots that fall onto the metal generate a much lower response. And that's not surprising. That's because the laser is not able to penetrate through the metal and lead to any effect on the silicon. So that's a sort of go, no-go indication. On the left-hand side is a plot of some data we obtained last year on one of these devices, which shows a number of different traces using different pulse energies. So allowing laser pulses to impinge on the device, but giving those more or less energy, and then plotting that against the magnitude of the transient against time, as shown there. And you can see here that changing the laser pulse energy is analogous to changing the LET of an ion beam. The magnitude of the response increases, the duration of the response increases. That's exactly what you would expect when using ions with different LET with an ion beam facility. Now, looking at the second example, I'm showing here the response of a voltage regulator device. This is a much larger device, and you can see that we have overlaid a number of spiral scans onto this device. They appear on this image more or less as hexagons as they've been tessellated, and you can see that there's quite a number of those spread across this device. Exactly the same process. Run the laser scan, look at the output of the device, the impact of those laser pulses on the device. And what we've done here, we've color-coded different regions of the device and color-coded on the right-hand side the response to the pulse. Plotted here the magnitude on the vertical axis and the duration of the pulse on the duration of the transient on the horizontal axis. And some very interesting structure starts to appear. You can see by the different colors shown here that there are characteristic responses in terms of both magnitude and duration in certain regions of the device. Now, that is something that is very, very useful information to the designers of the parts. They can find ways to improve the performance of the design by focusing on perhaps the highest magnitude or the longest duration responses, and identify where perhaps the weak areas are, and then for the next iteration of the design to improve those parts of the device. Next example I'll show is for memory mapping, and this is again useful for designers of parts, but also if you're looking at reverse engineering a part to understand how a part works, how it's been designed. This is quite an interesting technique. At the top, you can see the initial output of the laser scan, quite a large spiral array here, and there's really not any clear pattern that's come out of that. And that sort of suggests that any sensitivity, any changes in sensitivity across the device are happening on really quite a small scale. So we took those results and we started to analyze them by color coding the data according to the value of the address bits. And that started to yield some interesting pictures. You can see on the bottom right here that patterns coming out of the data. And what we believe is happening here is that the physical, really fine scale organization of the memory is coming out. It's becoming visible as a result of this kind of testing, and being able to see where individual bits physically are located within the device starts then to enable you to link the virtual and the real physical layout of the devices. So there's a huge amount of analysis can be done around that kind of data. Okay, so a couple of more slides left now. Just to look at the broader application of using a laser single event effects data on radiation testing. Using a pulse laser lets you try many different configurations of the device that you would not have the time to be able to do with an ion beam, whether that's bias or circuit arrangements. There's much more flexibility because you have the time to be able to do it. That means you can really define the safe areas of operation of a device much more tightly, much more closely. You can maximize that SOA because you can define the boundaries with much greater confidence. Perhaps a minor issue, but a minor application, but really a very, very useful one, is that you can use the laser system to verify that your test board is working properly before you go to the cyclotron. You can use it as a fault injection tool, and you can also use it to identify what is the worst case bias condition, the worst case arrangement of the device before you go to the accelerator. Both of those enable you to make really best use of that really expensive and scarce resource of ion beam time. And also touched on, you can use it to give you some robust data on those rare events. More broadly, then, cosmic rays induced single event effects are very well known in space, but they also affect components at all altitudes through the atmosphere down to sea level. Typical applications outside space where this technique is used and can be used are where you have very dense digital devices. Certainly manufacturers of servers and very highly sophisticated digital devices pay a lot of attention to cosmic ray effects. Lasers can be a very useful tool for helping those manufacturers. Large junction high voltage devices are known to be susceptible to cosmic ray effects, and manufacturers of these devices do spend a lot of time analyzing cosmic ray effects. Kind of applications, very heavy industry where lots of power is involved, or there are safety critical aspects to consider. So trains and planes cover both of those areas, and maybe some parts of critical infrastructure where you want to really be absolutely sure that a single event effect is not going to cause you a problem. Then you will want to quantify the risk, and lasers can offer a way to do that. So my final slide, just to summarize, we've seen that the space is a really hostile environment for electronics in some places at some times, and you may not know whether you're in one of those or not in advance. Single event latch-up is the most impactful kind of event that can lead to the failure of a mission within moments of deployment. It can happen very, very quickly, and then obviously there is no warning of it. Testing with an accelerator going to a cyclotron is expensive. It can take a long time, and pulsed laser testing offers a much faster approach, and it certainly is better suited to screening of parts. So if you're looking at using COTS parts, screening of those with a laser is an absolutely ideal approach to at least do some level of mitigation of your risk. That'll put you in a better position than doing no testing at all. And that combination, for me, it makes that kind of radiation screening available to many, many more missions than would otherwise be the case. Not just those who have deep pockets and lots of time. But laser testing also opens many other doors. It enables you to perform investigations that are simply not possible with accelerators. And we're really only just beginning to understand the range of possibilities that are now available to us with pulsed laser systems. So thank you everybody for listening to this presentation. I would be very happy to take any questions you may have on the topic or on any of the slides that I've presented. Feel free to ask me any questions.